Hello everyone, welcome back to my channel. So today I'm going to open your eyes to something very powerful that's all around us all the time, but we just don't know, and that is graphs. So it's not the boring math class kind, but the kind that powers the social media. Social media feeds helps you find the fastest route to work and even determines which pages shows up first in your search results. Sounds crazy, right? Well, buckle up because by the end of this video, your mind will be blown by how fundamental graphs are in our everyday lives. So let me go through the real world applications first. So graphs are not just abstract concepts. They are the unsung heroes of so many technologies we use every day. So think of how social media networks connect millions of users, showing you who is the friends with who, or how Google ranks web pages based on the links, helping you find the most relevant information. Even your GPS uses graphs to calculate the shortest path from point A to point B, navigating through the maze of streets and highways. So this was all about the real world application of graphs. So now let's go and understand what the basic fundamentals are for the graph data structure and how we can implement these in our applications and in our code. So let's go to the definition first. Graph is a collection of nodes between edges with the edges between them. So whenever you have a graph, it will have edges and vertices. I'm going to show you how the actual graph looks like, but this is just a brief overview. Graphs are used to represent relationships and are fundamental in computer science, biology, social science, etc. So again, we are using graphs all over the place. So let's say you're driving something from Uber. So Uber driver will have to look at the maps, right, to find the shortest route possible for your house to deliver the food. Or so let's say there is an Amazon truck just which is going from warehouse to all the people for delivery. So they will have to go through that algorithm first. That application will have to go through that algorithm first, such that it can give all the delivery locations one by one according to the shortest distances available. So that's how these things work in transportation networks as well. Okay, so what is graph? So here's the definition of graph. It consists of set of vertices V and set of edges E connecting to the pairs of vertices. So if you can see that here's the point A and here's the point B. Here's point D, point E, point C, and so let's say point A. Point A is my house. Point B is somebody else's house. Let's say it's my friend's house. Point D is somebody else's house, and let's say C. So C is a so let's suppose that C is somebody who is starting off to deliver all the packages to all these houses here. So they are starting from here, here, and here. So we will have to make an algorithm in such a way that it goes to the shortest distance first. So maybe it can go to B first, or maybe it can go to E first because the distances are equal. So C will go to the B first to deliver the package. Then it will go to the B, and then it will go to D, and then B, and A, and such. In such way, it will find the most efficient way to order the packages. Sorry, to deliver the packages. So here's how it works. So these are the edges. So A and B, maybe you can say that there's a distance between them, and then you can call them edges as well. Okay. So types of graphs. So there are two types of graphs. There are lots of graphs actually, but here we have undirected graph and directed graph. So V1, V2, V3. You can see that there is no direction between this. So you can either go V2 to V1, or you can either go V1 to V2. It doesn't really matter in undirected graph. But if it is a directed graph, V1, V2, so you can say that it is pointing towards V2. So you can go to V2 from V1. So V1 to V2, but you can't go otherwise. You can't go otherwise. You can't go V2 to V1. So that's the significance of directed graphs. So weighted graphs and unweighted graphs again. So it will have some weight, weight specified here, AB 4, AC 10, CB1, and it could be the distance in most of the cases, and they are specifying it as weight. And here's the unweighted graph. If you'll see that AB, there's nothing between that. There's no distance between that. A and C, there's nothing between that as well. So that's how unweighted graph looks like. Okay. So again, so graph representation, we will have to understand the fundamentals and basics of how we can represent the graph in order to write the code. So right, we are storing graphs somewhere. It's not like we're drawing the graphs in code. We will have to store our graphs in somewhere in the code. Like we can store it in the array, we can store it in the linked list, we can store it in the tree as well. We can store it in the matrix like this adjacency matrix. So there are some different ways to do it, and there are two most popular ways to store the graphs, and those are called as adjacency matrix and adjacency list. So adjacency matrix. So first of all, a 2D array where each cell ij indicates if there is an edge between vertex I and vertex j. Easy to implement, fast edge lookup, and is space sufficient for the sparse graphs. So we'll have a matrix, we'll have a 2D matrix defined. I'm going to show you in my whiteboard how it actually looks like and how you can plot the graphs for the adjacency matrix. But you can just, for now, you can just understand that in an adjacency matrix, we are going to store all the edges and vertexes in a 2D array. That's all you can that's all you can keep in your mind for now. Okay. Now, next is adjacency list, an array of lists. Each contains all the vertices adjacent to a vertex. It is very space sufficient if it is not if it is not a big graph, right? For the sparse graphs, you can say that for the small graphs, it is very space sufficient because it is easy to iterate over the neighbors, right? But if you want to have the edge lookup, it is very slow as compared to the adjacency matrix. What do I mean by edge lookup? Edge lookup is something that let's say there are 2 points A and B, but I want to find out that are they connected or not? Do they have edges or not? That's where edge lookup comes into the place. Edge lookup becomes very easy in the case of adjacency matrix. You can also do it with adjacency list, but it's just that it will take more time. So whenever we are writing code, we're always looking for something more efficient, right? So this was how we can define our basics of graphs. I'm going to show you how adjacency lists and adjacency matrix looks like. And that will be all for now. And then from the next video, I'm going to cover BFS and DFS. These are the two algorithms that is very important for the search. And we will go through all the code into the next videos. Let me bring the whiteboard first here, and then I'll show you how these things actually work. So if you can see on my whiteboard, here I have an example of adjacency list for now. For the first example that I'm going to cover is adjacency list. Now see, here we have graph here, 0 to 2, it's connected, 2 to 3, 3 to 1, and 1 to 2. So now we'll have to go and find out how we can get the points in our scatter plots, right? So here, if I will add the text, so first of all, if we have a look at it, we can determine that we have 4 vertices, 0, 2, 3, 1, and at the same time, we have 4 edges. Okay, so 4 vertices and say 4 edges. So what vertices we have? We have 0, we have 1, we have 2, and we have 3. Okay, perfect. Now see, we'll have a look. We'll have to go one by one. What is the point that we can go? Where is the point that we can go from 0? It's just 0 and 2. So it will be 0, 2 here. Okay. And then next time we will have for one, it will be 1, 2, and it will be 1, 3, right? And then for, if we go here, next 2, we have 2, 3, and 2, 1, and we have 2, comma 0 at the same time, right? And then we will go to 3. 3, we can say that we have 3 comma 2, we have 3 comma 1. That will be all. So these will be the lists that we are going to store in an array list, right? So we are going to combine all of them together, and then it will be called as lists of lists. And what do I mean by that? See, we will have a list here. Let me go create this. Right. So here I have list 0, 1, 2, and 3. So 4 elements I have, right? So inside these lists, we are going to have these lists, right? So 0, and then for 1, it will be this inside. So inside this, we have 2, and inside this, we have this 3. Okay, perfect. So this will also be stored in the lists. Now we are going to combine all of the lists together, and then we're going to display it in the graph. I know it sounds very complicated, but once we start coding, it will get easier. Okay, so this was adjacency list. Now, what about adjacency matrix? So for our adjacency matrix, whenever you will encounter an edge between 2 points, you're just going to write 1 inside the matrix. All the other elements inside the matrix are going to be 0. So let's say it is 0, 2, right? So we know that there is an edge between 0 and 2. So what is going to happen in matrix? Element 0 and element 2 is going to be equal to 1. And then when we will know that there is an edge between, say, 2 and 3, it is going to be 1. Same with the other points as well. Same with the other edges as well. So whenever you see something like that, you just straight away put it as 1. All the other elements are going to be 0. So this was all basic and theoretical explanation of how graphs work and how we can represent and store the graphs. In further videos, I'm going to cover how we can code, what are some basic operations, and how we can actually implement these in our real life applications. So thank you so much for watching, and stay tuned for the further updates.